Welcome to part one of our four-part series of HSPF training videos. I am Doug Bayerlein, co-founder of Clear Creek Solutions. In part one of this series, I'll walk you through an introduction to HSPF continuous simulation hydrology. Let's get started. Part one is an introduction to HSPF continuous simulation. It is an overview of how continuous simulation hydrology works. It's followed by part two, which describes the specifics of how runoff is calculated for both pervious and impervious land, and then routed through conveyance systems, which can be streams, lakes, stormwater systems, etc. Part three is all about making sure that the model results reflect real-world conditions. And finally, part four is how to use HSPF to solve stormwater problems. Here at Clear Creek Solutions, we use HSPF as the computational engine in all of our stormwater software packages. In many jurisdictions in Washington, Oregon, and California, this is the required way to demonstrate compliance with local stormwater regulations. But even when HSPF continuous simulation hydrology is not required, this methodology is a powerful tool to evaluate and solve stormwater and flooding problems of all types anywhere in the country. Now, continuous simulation hydrology is different from single event hydrology, and I think that's important, and we'll talk more about that as we go through this. We will be using time series data to do our modeling. So in other words, we need to have a long period of rainfall data to use as input into our model. We'll talk about the major modules that are available in HSPF and how to develop a simulation plan to basically solve whatever sort of problem you're trying to work on, and then potentially when not to use HSPF. So the way HSPF works is that it models all of the components of the entire hydrologic cycle. So what this means is that we have rainfall or precipitation data as our input. That drives the whole hydrologic cycle. So when it rains, the first place that water lands is on the vegetation. So this is what we call interception storage. So if you're standing underneath a tree and it starts to rain, you're going to stay dry for a while because that tree has a certain amount of interception storage. And if it rains long enough and hard enough, eventually that will fill and the water will start dripping on your head and then get down onto the soil surface. Now, this is true for any type of vegetation. Different types of vegetation have different amounts of interception storage, and HSPF models that and keeps track dependent upon the type of vegetation you have. Once the water gets down onto the soil surface, then depending upon the soil characteristics themselves, that water can either become surface runoff or overland flow, or it can go into the soil and become shallow subsurface runoff, or what we call interflow, or it can go deeper into the soil and eventually come out as groundwater or base flow. Now, that's only half of the hydrologic cycle. The other half is the fact that we have water going back to the atmosphere either as evaporation from water bodies or evapotranspiration. Evapotranspiration is water that is sent back to the atmosphere from the plants, and so that is a major component of the hydrologic cycle. So what we're going to be using continuous simulation to do is we're going to generate multiple years of hourly runoff data from multiple years of hourly rainfall data. And then this gives us then a long record of information that we can use to do whatever type of analysis we're interested in. That's how continuous simulation works. So we modeled the entire water cycle on an hourly or shorter time step for multiple years. And we could do this for 5 years or 50 years. It all depends upon what we're trying to do and how much actual rainfall data we have as input. The model, every single time step models the changes in our soil moisture, evapotranspiration, and runoff. So it tracks all this information all the time, everywhere. Now it generates three types of runoff. As I mentioned before, we have surface runoff, which is the same thing as overland flow. We have interflow, which is that shallow subsurface runoff. And then we have groundwater or base flow, which is the deeper subsurface runoff. So we can then send that water wherever we think is appropriate in our model. Now, continuous simulation hydrology is different than single event hydrology. So it is based upon how we model the hydrologic cycle rather than making a series of inaccurate or inappropriate assumptions that are used in the single event methods. Single event methods were developed when all we had was a slide rule to do our calculations, so we had to keep it simple. With computers that we have today, we can do a lot more calculations a lot more quickly and really better represent what's going on in the hydrologic cycle. As a result, we can include all the major components of the hydrologic cycle, which we do not do in the single event hydrology methods. And we can answer questions that single event methods cannot answer. If we're looking at things like flow durations, how long flows are above a certain level, we have the long-term record to do that. We can actually compute flood frequency based upon the statistics of how many big floods we have, rather than just making assumptions. And we'll talk more about that here in just a second. So what single event modeling does is they have to make assumptions. And one of the assumptions that they make is that the runoff frequency is the same as the rainfall frequency. In other words, the 100-year storm causes the 100-year flood. Now that can be true, but it doesn't have to be true. That depends upon a lot of things. And so that assumes that the antecedent soil moisture conditions are always the same at the start of every storm event. But that's not true in real life. In real life, you can have situations where you have a long dry period where the moisture in the soil is very low, and then you get a heavy rainfall, and you might generate very little runoff. Or you may have a condition where you have the watershed is very saturated because it's been rained on multiple times, and now you have a big rainstorm event, and it produces a lot more runoff as a result. So single event models don't take that into account. They assume that there's always going to be dry periods between storm events, and there's never going to be back-to-back storms that are going to then basically make the situation worse when the next storm comes along. And they also make the assumption that every storm shape and rainfall distribution is the same, that the storms are all going to have the same look, the same way of how much rain occurs over the period of the storm event. And in real life, that just doesn't happen. So what continuous simulation does is that it uses the actual rainfall data that has been historically collected that represents real world conditions. As a result, then we can compute runoff and compute the frequency that runoff occurs for major peak events using this multiple years of simulated hourly runoff data. We compute what's happening in the soil every time step. So we don't make assumptions about what the antecedent moisture conditions are. We actually calculate what the moisture conditions are. And as a result of all this, we have the ability to compute runoff based on the actual historic rainfall data. So we can see how the runoff varies by storm event based upon actual historic storms. So this means that we use real storm shapes and rainfall distributions, and they all do not necessarily look the same as what a hypothetical storm looks like.